Guys, Mr. Peters here. Going to be talking to you about the limits of infinite sequences. So, in previous sections, we've talked about sequences some, and you should feel kind of comfortable with what they are, what they look like, right? So, these are a consistent group of numbers that either grow or decrease at a constant rate of either addition, if it's arithmetic, or multiplication if it is geometric, right? And so if we have an infinite sequence, that's just going to be a sequence that doesn't have a last term, right? Sequence that goes on and on and on, right? So consider the one that I have here in red. I've got 1/2, 1/4, 1/8, 1/16, right? And that we can see that is just taking each previous term and multiplying it by 1/2, right? So to find the first term, I could say n is equal to 1, right? To find t1, I would set n equal to 1. If I wanted to find the second term, I'd set it equal to 2. The third term, I'd set it equal to 3, etc., 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 right? So as n increases, I see that my term gets smaller and smaller and smaller, right? It approaches 0. This is a mathematical concept that has been defined as a limit, right? So we are going to be talking about the limits of infinite sequences. What do these limits approach as n gets larger and larger? Not only as it gets larger and larger, but as it approaches infinity, right? So what we write here, we write the limit as n approaches infinity, and that right there is supposed to be a little arrow, so I'll try to make that a little better. All right, so as n approaches infinity of 1/2 raised to the n, right? So this right here would be our limit. This is how we would write it, and that reads the limit as n approaches infinity, as n gets larger and larger and larger, of 1/2 raised to the n. And we can actually find this and show, hey, you know what this is equal to? This is equal to 0. As n gets bigger, our sequence approaches 0. Often the best way to find a limit is to go ahead and substitute a really, really big number in for n, right? So let's look at a here. I've got the limit as n approaches infinity of the sine of 1 over n. So why don't we just pick a random number for n? Why don't we take 100? Okay, let's let n equal 100. So what we have here is the sine of 1 over 100. Now, 1 over 100, that's just equal to 0.001, right? And the sine, or sorry, not 0.001, that's going to be just 0.01. So as n is getting larger and larger, it approaches 0. And so does sine of 1 over n, right? So I can see that 1 over n approaches 0 as n gets larger. Same with the sine of 1 over n. This also approaches 0. So we can say the limit as n approaches infinity of sine of 1 over n, this is equal to 0, right? It approaches 0. Well, what about the, let's look at b over here. I've got the limit as n approaches infinity of 0.99 raised to the nth power. Well, let's just pick a big number and plug it in for n, and let's see what happens. Let's say, what if I had 0.99 and I raised it to the, I don't know, 1,000th power. What does that equal? Well, 0.99 raised to the 1,000th power is something like 4.3 times 10 to the -5th. That's a tiny number. Well, what if I picked an even bigger number, right? What if I had like 0.99 raised to the 10,000th power? Well, that's 2.2 times 10 to the negative 44. As n approaches infinity, as n gets larger and larger, we see that this gets smaller and smaller. It actually approaches 0. So we can state that the limit as n approaches infinity of 0.99 raised to the n is equal to 0. This leads us to one of our theorems, right? If we're looking at the absolute value of r and it is less than 1, then the limit as n approaches infinity of r raised to the n, right? So that r is just representing whatever is raised to the power of n. That is going to be equal to 0, right? And we can see that when we reference practice problem B up here, right? We see r, which is 0.99, that's less than 1. So when I raise that to the power of n, as n gets bigger and bigger and bigger, this limit approaches 0. So this is one of our theorems that we're going to be using pretty heavily. All right, so let's look at some more examples here. Let's say we move away from just raising to the power of n, and we start looking at some crazy expressions, right? I've got the limit as n approaches infinity of n squared plus 1 divided by 2n squared minus 3n. Now, let's think about this. As n gets bigger and bigger and bigger, how important is this? How important is that? How important is this? Right? We're talking about raising something to a square power, right? I'm talking about raising something to a square power in both the numerator and the denominator. So if I take 100 and square it, right, that gives me a large value. Does that plus 1 really change what my number is? Not really. If I take 2 times 100 squared and then subtract 3 times 100, well, yeah, that'll have a little bit of an effect. But what if I'm talking about n as like 3 billion, right? 3 billion squared is a massive number. So subtracting off 3 billion from that is not going to have that big of an effect. So whenever we are dealing with the limit of an expression like this, what we are able to do is rewrite n squared plus 1 divided by 2n squared minus 3n. We can rewrite this. They're not equal, but we can change this to just be, well, n squared over 2n squared. As n approaches infinity, this expression approaches this expression. They get closer and closer as n gets larger and larger. Now, if I'm just looking at this, what cancels out? Well, the n squareds cancel out, don't they? I could look at this and say, well, this is actually equal to 1 over 2. Right? We can, as n gets bigger, we can take these little guys right here and just kind of say, we don't need them. Because n is so big that the addition of 1 or the subtraction of 3n has no effect on what our limit looks like, right? So we are able to reduce this down to n squared over 2n squared, which then can be reduced down to just 1 over 2. And this is one of our really cool tricks that we're able to use. When dealing with these limits, we just want to find the highest power in both the numerator and denominator, and then reduce from there. So guess what? The limit as n approaches infinity of this expression is just 1/2. Which I think that is just fabulous and super cool to see. All right, well, let's look at our next problem over here to the right. The limit as n approaches infinity of 5n squared plus the square root of n divided by 3n cubed plus 7. Now again, how important is the square root of n? How important is this 7? They're not. These are not important. because they're such small values as n gets bigger and bigger and bigger. So I'm going to rewrite this as just 5n squared over 3n cubed. Now, as n gets larger, which one of these, the numerator or the denominator, is going to get bigger? Well, they're both going to get bigger, but which one's going to get bigger faster? The denominator here is going to grow much faster. And when the denominator grows faster, what does this value approach? Well, it's just like this problem that we had up here. Sorry for the scrolling, right? It's just like this problem up here. I have 1/2, 1/4, 1/8, 1/16. My denominator is growing very quickly. So what do I approach? I approach 0. So it would make sense that when looking at this expression here, if the denominator is growing faster than the numerator, we can say this approaches 0. When, oops, I wanted to change colors there. When the denominator grows faster, the limit approaches 0. So this limit is equal to 0. Obviously, I know the next question you guys want to ask is, well, can we have a sequence that has no limit? Can a sequence have no limit? Well, I've got an example for you guys. All right, it's going to look a lot like one of our previous examples. And it reads, let's have the limit as n approaches infinity of 7n cubed over 4n squared minus 5. Looking at this expression, 7n cubed over 4n squared minus 5, as n gets bigger and bigger and bigger, as it approaches infinity, and we're not just talking 100, 1,000, 10,000. We're talking like, 100 billion, 100 trillion, 18 quadrillion, whatever. We're talking massive numbers here. Which is growing faster, the numerator or the denominator? Well, since my numerator here has a higher power, my numerator is growing quicker. Numerator is growing quicker. So previously we said, well, hey, when the denominator grows faster, the limit approaches 0. So what are we approaching when the numerator grows quicker? Well, it doesn't seem to really approach anything, right? It's just getting to be bigger and bigger. There is no biggest number to approach. So we state that this limit approaches infinity. We say, well, there is no real limit. It just approaches infinity. And that's all I have for you guys. If you've got questions on the problems that we end up posting, don't hesitate to reach out. Best of luck.